In this section, we consider various ways of measuring AC quantities. The usual D'Arsenal galvanometer has too large a moment of inertia to follow the instantaneous values of an alternating current, except possibly at extremely low frequency. The galvanometer, you've got a very high frequency, a standard meter is not going to work. At ordinary frequencies such as 50 Hz, household power, something that's only oscillating at 50 cycles a second, you'd probably be able to see the meter and then measure those two extents, and that would actually work, but that's only for low frequencies. This just is talking about how you find the average value of a quantity over a time interval from t equals 1 to t equals 2. The equation may be interpreted graphically. The integral represents the area bounded by the curve of function of t and by the two vertical lines, t1 and t2, which I've just said. The product, FAV, times t1 minus t2 is the area of the rectangle of height, FAV, so this rectangle, and base, t2 minus t1. Thus, FAV is the height of a rectangle having the same area as the area under the curve between the same two values of t. So let us apply this definition to a sinusoidal varying quantity, for example a current given by I equals I sine Wt. The period tau is given by t equals 1 over f, and that is 2 pi over the angular frequency. Here we've got t2 minus t1, well that's the same as 0 to pi over w, that's the total period there. If you invert that, you're going to get omega over pi, and then you place those on the integrals and you've got I sine Wt. Now if you just calculate that, the integral of that is cosine. You can just work that out yourself. We end up with the average value of the current is given by 2 pi times the maximum current possible. This is the maximum value here, maximum value, equals the area under one loop of the sine curve, so that's one loop. The average current for a complete cycle of any number of complete cycles, that's going to be 0, because the one underneath is going to cancel with that one. Hence, if a sinusoidal current is sent through a meter, the meter reads 0. Such a meter, though, can be used in an AC circuit if it is connected in the full wave rectifier circuit shown in this diagram. This is an alternating voltage. You can measure the current here by setting up these diodes, and this is like a bridge rectifier. You can see if the current in one cycle is moving in this direction, it's going to move down there and it's going to move through the galvanometer. It's not going to move up there because the diode's against it, so it's going to move through, and then it's going to move through that diode. It's not going to move down there, it's going to carry on and back. And if it's going the other way, so let's say we're going the other way, then when we're going the other way, it's not going to go up there, it's going to go up there, and it's not going to go against that one, it's going to go the same direction again. So no matter which way the alternating voltage is, the current's always going to go in the same direction. We can set something like this up, and then we're able to measure voltages and currents with a normal galvanometer. Thus, for a sinusoidal source, the current through the meter has the waveform shown here. The current amplitude I, when the meter deflects full scale, we can just use this, because once we read that off, we know this, therefore we can get a value for the actual maximum current by using this average value. So that's the utility of finding this. We're able to then use a meter and measure AC voltages by averaging out these values. So for example, if the average value is measured to be 1 amp, then the actual maximum current will in fact be 1.57 amps.